Okay, so we will continue with the file system implementation discussion. So far we have seen how we can allocate disk blocks to files. Okay, we have seen several strategies for that. Contiguous allocation, linked allocation, and so on. Basically those strategies also tell you how we can locate the disk blocks that are allocated to a file. Okay, given a file name, all right, you can locate first the corresponding file control block on the disk, which will give you further information about how you can locate blocks that contain the file content. Okay, so far we have seen some methods for that. Those methods were contiguous allocation, linked allocation, file allocation table, index allocation, and so on, right? With those methods we can find out what are the data blocks of a file. Okay, then you can retrieve the content sitting on those data blocks while reading a file. Okay, so now we will look to a different problem. So when we want to allocate a new block to a file, assume the file is growing. Okay, you are writing data to the file. So the file system would like to allocate a new data block to the file. Okay, so how can we do that? How do we know which block on the disk is free? So when you want to allocate a new block to a file, you have to find out a free block on disk. Okay, and then you have to give that to the file. That means the number of that block, or block number, or address of that block has to be inserted into the, for example, index table for the file, or into the file allocation table, and so on, right? So that you are giving that block to the file. But how can you find out such a free block? Okay, so this is the topic of the free space management. How can we manage the free space on the disk? How can we keep track of the free blocks of the disk? Okay, this is the problem. So, and we need this information, the free block information, when we want, for example, to allocate new block or blocks to a file. At that time, we would like to find out which blocks are free, or which block is free on the disk. Okay, and then we can allocate that block or those blocks to the file. Okay, so how can we know which blocks are free on the disk? We will see some strategies for that now. There are several methods to keep track of the free blocks of the disk. Okay, these strategies are bit vector method, or bitmap method, linked list method, grouping method, counting method, and so on. Okay, so we will look to each of them now. So we will start with the bitmap method. Okay, that can be used to keep track of the free blocks of the file. Okay, to know the whereabouts of the free blocks. So the idea is very simple. We have a bit vector or bitmap like that, bitmap like this. Okay, where we will, on that bitmap, we will have 1 bit per block of the disk. Okay, indicating if that block is used or free. If there are n blocks, there will be n bits in the bitmap. Okay, there will be 1 corresponding bit in the bitmap for every block. So if the block is free, the corresponding bit can be, for example, 1. But if the block is used, allocated to some file, then the corresponding bit value may be 0. Okay, or vice versa. Okay, the corresponding bit can be 0 for a free block, or 1 for a used block, or vice versa. That means the corresponding bit to a block may be 1 if the block is free. It can be 0 if the block is used. Okay, so for example, we have a small disk here that has 12 blocks. I can put, for example, the bitmap in some block. Let's say this block 0 contains the bitmap. That gives information about the free blocks. Okay, so in that bitmap I will have 1 bit for each block of the disk. So this bit will correspond to block 0, that bit will correspond to block 1, that bit will correspond to block 2, that bit will correspond to block 3, and so on. So the last 4 bits will correspond, for example, to these last 4 blocks. Okay, so assume this gray indicates that the block is used. Here the block is free. Okay, so this is a used block, used block, used block, used blocks, and free block. Okay, so for each used block, the used blocks, the corresponding bit should be 0, right? For a free block, the corresponding bit should be 1. So now by looking to the bitmap, without looking to the rest of the disk, you can understand which blocks of the disks are free, which blocks of the disks are used. Okay, so if you want to now find out a free block, because you would like to allocate a new block to a file, then you can just look to the bitmap. Okay, so for this particular simple example, which block is free? The first block that you will encounter while searching the bitmap, it will be block 5, right? So 5 or 4? Right, it is the block 5, 5th block, but actually it is the index of that block will be 4, right? So block 4 is the first free block, so you can allocate, for example, that to a file when the file would like to have one more block. So this is the basic idea. We can keep track of the free and used blocks by maintaining a bitmap, okay? So when you, for example, allocate this block, then you have to set the corresponding bit to 0, so that now the corresponding bit will indicate that the block is used, okay? So that means if the disk has n blocks, okay, then we need a bitmap that has n bits, right? So for each block of the disk, we have a corresponding bit. So for the ith block of the disk, the bit value can be 0 or 1. If it is 0, we can consider the block is used. If it is 1, we can consider the block is free, okay? Or vice versa. This is just a convention. So now, if we have a bitmap and would like to find a free block, basically we would like to allocate a free block to a file and we are interested in the number of that free block, how can we find out the number of that free block? So we have to search the bitmap, right? Starting from the beginning of the bitmap, you can just look to the bits, or you can do an efficient search. You can look to the bitmap in words, okay? One word at a time. So what you can do, you can just get this word, see if it is 0 or not. If it is 0, that means all the blocks, corresponding blocks are allocated, okay? So you can search for words until you find a word that is not 0, okay? So we can start searching from the beginning of the bitmap, search for the first one. So what you will do, you will skip the 0 valued words until you hit a word that is non-zero, right? So then the offset of that one in that word has to be added to the word length multiplied by the number of words skipped, okay? Basically, the corresponding block number to that bit, that is 1, will be what? Number of 0 value words multiplied by number of bits per word plus offset of the first 1 valued bit, okay, on that word. So basically for this particular example, the number of 0 valued words is 3 and word length is here 16, okay. So 3 multiplied by 16 plus the offset of that bit is 8. You add 8 and you find that the position of that bit is 56. That means the corresponding block is block 56, okay. So this is the free block, okay. You can now allocate that block to a file. So that block now becomes used. So you have to change that 1 to 0, okay. Is it clear how we can search for a free block? So this is how we can use the bitmap. So the idea is very simple. So now, what is the cost of using a bitmap? For the bitmap, to store the bitmap, we need space on the disk, okay? So it causes extra space to be used. What is the extra space amount? You can compute that, right? It depends on the size of the disk, the block size, and so on. So assume we have blocks that are 4 kilobytes long. Each block is 4 kilobytes, okay? Assume we have a disk that is 1 gigabyte disk, okay? 2 to the power 30 bytes. So then how many blocks we will have on that disk? Disk size over block size will give us the number of blocks on the disk, right? So 2 to the power 30 over 2 to the power 12 will give us 2 to the power 18, which is the number of blocks on the disk, okay? Now, since for each block we need a bit, so how many bits do we need in the bitmap? 2 to the power 18 bits required, right? So we need that many bits in the bitmap. So if I ask you what is the storage need for those many bits in terms of kilobyte, so that many bits make 2 to the power 18 over 8 bytes, okay? Each byte is 8 bits, right? 2 to the power 18 over 8 will give you the storage requirement in bytes, and if you divide it by 1024, then you can find out the storage requirement to store that bitmap in kilobytes. So the result is 32 kilobytes. So you need 32 kilobytes of disk space to store that bitmap, okay? So this is the extra storage need, okay? So you cannot store something else in those 32 kilobytes. It's not that much for such a disk, okay? But assume the disk is very large. Let's say, for example, 256 gigabyte disk or 300 gigabyte disk, then you need 300 times 32 kilobytes storage, okay, on the disk. So What are the other advantages of the bit vector, using bit vector? So it is easy to get contiguous files. It is easy to allocate blocks to a file in a contiguous manner. Because by looking to the bitmap, you can immediately see, okay, by searching the bitmap, you can see which blocks that are free are next to each other. So if you want, for example, to allocate 3 blocks to a file, and you want those 3 blocks to be next to each other, and if this is the bitmap, then which blocks you would allocate? One alternative, for example, could be allocating this block, and that block. But you want those 3 blocks to be next to each other if possible. Then you can, for example, allocate those 3 blocks here. That block, and that block to the file. In this way, you will have those blocks of the file next to each other. Okay? This is important while you are reading the file sequentially. You will not do much disk seeks while going from one block to another if those blocks are clustered together. Okay? But of course, we require extra space on the disk to store the bitmap. Any questions about the bitmap method? So it's very easy. For example, this method is used in Linux file system. Okay? All right. Let's look to another method. Alternative method is using linked list of free blocks. So you have free blocks on the disk that are free, right? That can be allocated to files. But the idea is very simple. Just link them together. Those free blocks will be linked together. One free block will have a pointer pointing to next one. Okay? A pointer can be just 4 bytes long, a disk address or block number, pointing to the next block, okay? Giving the block number of the next block that is free. Each free block will contain a pointer or will contain the block number or address of the next block that is free, and so on. Okay? So in this way, you can just link the free blocks together, and you can also store a pointer to the first free block. That pointer can be stored, for example, in some special location on the disk. For example, in the super block. Okay? The first block of the disk partition can be super block, can be used to store some information about the file system, including, for example, such a pointer pointing to the first free block. Okay? So in this particular example, for example, we have such a disk. These are the used blocks. This is a free block, used block, free block. So for example, this is block 4 that is free, block 5 that is free, block 7 that is free, block 9 that is free, block 10 that is free, right? So what we can do is that block 7 may be the first block that is free, so it's pointed by the super block, and then it can include a pointer pointing to the next free block. So at the time, for example, this pointer is installed, this block may be used, so this pointer may be pointing to here. So block 4 is free, and it has a pointer 7, that means the next free block is block 7, okay? So then this may become free and so on. We can have a pointer pointing to here, and this may have a pointer pointing to block 9, and block 9 may have a pointer pointing to the next free block, which is block 10, okay? In this way, for example, I can, if I want to learn all the free blocks, I can start searching from here and follow the pointers, find out all the free blocks, okay? If I need to allocate a block to a file, then what I should do? If I want to allocate just one block, then I go to the first free pointer. What is that? It is 4. So I go to the block 4 and allocate that one to the file. Block 4 will be allocated to the file. And here, so this will no longer be free. It will be used by the file, right? So this will no longer be the first free block. Which one will be the first free block after this? If I allocate this to a file, which one will be the first free block? 7, right? So that means I have to change this pointer to point now to here. Okay? This is the only thing that I have to do. If I want to allocate any block, I just allocate the block pointed by the first free pointer, and then I change the first free pointer to point to the next free block. Okay? This is the thing that I want. So just finding out the free block is very easy. Okay? But assume you would like to allocate 2 blocks to the file. So which blocks you will allocate for this particular example? You will allocate that block, block 4, and also block 5 or 7? 7, right? So you are not allocating a nearby block, even though there is a nearby block, right? So this is a problem. So the linked list may be just traversing the disk in any order, okay? And therefore, it is not easy to, by just following the linked list, it's costly actually to find out a contiguous chunk of blocks to be allocated to a file. You have to traverse the linked list and so on, which is a costly operation because every pointer is a disk pointer here. You have to go to that block, extract the pointer here, and then go to the next block, extract the pointer here, there, and so on. Okay, so every following of the pointer requires a disk access. A disk access is a very slow operation. It will take 20 milliseconds. Okay, so finding a free, so for example, a contiguous chunk of free blocks is not easy with this method. Okay, to be allocated to a file. So cannot get contiguous space to a file easily. Okay, but of course we have now no waste of space even for the bitmap. We don't keep bitmap, right? Even these pointers do not waste space because they are actually in the free blocks. So when a block is allocated, all the space in the block is used. Okay. So here we keep a linked list, all right, that's actually occupying the free blocks. So therefore we are not wasting any disk space. Okay. We are not wasting any disk space. No space is wasted to keep track of the free blocks because the pointers are on the free blocks themselves. Okay. So this is another illustration showing the free space management using linked lists. So the free space links list head may point, for example, to block 2. This is the first free block. It is pointing to block 3, block 4, and so on. So by traversing the list, we can find out all the free blocks, but it's a cost operation. So in this way, we can know which blocks are free and so on. All right. Another strategy is grouping. Any questions about linked list? So another strategy is grouping. Here in this linked list, what we have is that we have a free block, keeping only one pointer to another free block. Okay. What we can do is that the idea is the grouping is that have a block containing many pointers to free blocks. Okay. So this is a block that can contain many pointers to free blocks. For example, in this particular example, it contains 2 pointers to free blocks. Block 82 and 127 is free. Okay. So we have another block that keeps free block information. Another block that keeps free block information. How many blocks do we need? Such blocks do we need? Depends how many blocks are free. Okay. So for example, this block keeps free block information. It tells that block 53 is free, 251 is free, 215 is free, and so on. Okay. And we can link those blocks together. We can link those blocks that keep free block information together, right? And we can have a pointer pointing to the first such block that is keeping free block information. So this first free, for example, or first block pointer points to a block that includes some free block addresses. So here we record the block number of that block. Okay, block 17 contains free block addresses, and 17 is recorded here. So if I want to now allocate any block to a file, I need to find a free block, right? What do? I follow that pointer. That pointer says that go to block 17. That will include some addresses, free block addresses. So I go block 17 and obtain, for example, this one. So block 82 is a free block, so I can just allocate that one to the file. So now that will be used. So 82 will be removed from here, okay? So then next time I will allocate that one maybe, okay? And so on. So then I will allocate that one maybe, okay? Then I will allocate that one maybe. So I will have some empty slots here into which I can put a free block address. So after I have allocated all these, what happens? This block actually is no longer, there is no need for that, okay? I can free that. So I can just free that. So now this block becomes a free block. I can add its number to here, okay? In this way, for example, a block containing free block pointers will get free when those pointers, addresses, or when the corresponding blocks pointed by those pointers will be used, okay? This is the method. This is called grouping. You just group a set of addresses or put a set of free block addresses into a block. How many addresses you can put? You need one address to point to the next block that contains free block information. So you cannot use that entry, but the remaining entries can be used. How many entries, such entries you can have depends on the pointer size. It can be 4 bytes. And on the block size, it can be, for example, 4 kilobytes. Then you can store 1024 addresses here. One address will be used to point to the next block that contains free block information. The other pointers, the other addresses, 1023 addresses can be used to point to the free blocks, okay? So basically, in one block, you can store 1003 free block addresses, okay? Any questions about this method, grouping? So another method to keep track of the free blocks, free space on a disk is the counting method. So this is similar to the free block pointer method. So besides the free block pointer in each block, we also keep a count, saying how many blocks are free contiguously after that free block. Okay? So here, for example, we have 2 contiguous blocks that are free. Here we have 3 contiguous blocks that are free. Here we have 1 and so on. Okay? So initially, for example, I can point to here by keeping the address of that block 3. Okay? The address of that block is 3. I can record 3 somewhere in my super block. That means this is the first free block. But besides recording the address of that block, I can record how many blocks after that is free. 1, 2 blocks are free. So I can actually keep that count also. So that means by looking to that information, I understand that starting from block 3, there are 2 blocks that are free. Okay? So then I can also record an information here, recording the address of the next chunk of free blocks. What is the address of next chunk of free blocks? 7, right? So I can record 7 here plus the chunk size, contiguous number of blocks, which is 3, okay? So I can come to this block and obtain that information, and then I can jump to here to reach out to those free blocks. There I can record, for example, the address of the next chunk, which is 11, and the size of the next chunk, which is 1, okay? In this way, I can again have pointers, but now the number of pointers that we will use is quite less compared to having a pointer to every free block, okay? So this is the counting method. Any questions about that? So this is all I want to say about the free space management. Okay. Do you have any questions? In the file allocation table method, for example, the free space management does not require any extra algorithm or structure, because the FAT itself can be used also to manage the free space, because the entries that are not used in the FAT file allocation table, they are considered to be free entries, free blocks, okay? Remember the FAT file allocation table? So here, for example, for the file allocation table, we have a file allocation table, 1 entry in the table for every disk block. So this entry corresponds to disk block 0. This entry corresponds to, for example, block 217, okay? So for a file, assume these are the blocks that are allocated to the file. That means for the file, we store the address of the first block allocated to the file in the directory entry. In the corresponding entry here, we store the address of the next block allocated to file, which is 618, right? In that entry, we store the address of the next block allocated to file, which is 339, okay? And there, this is the last block allocated to file. So the blocks allocated to file are this block, and that block in this order, right? So if, for example, you see an entry here where we don't have any valid block number, that means that entry is unused, okay? Then you can actually allocate that entry, the corresponding block, to a file. So then, that means a FAT itself gives you the free space information. You don't need any other structure like a bitmap or free space pointer and so on to keep track of the free blocks on the disk. The FAT actually can be used to manage the used blocks and also the free blocks, okay? Is it clear? Okay. So far we have seen the files, how the files can be mapped to blocks, how the blocks can be allocated to files, and how we can keep track of the blocks allocated to a file and so on, and how we can manage the free space on the disk, how we can know about the free disk blocks and so on. All right? So these are the basic algorithms that a file system should support, okay? These are the primary functions of a file system. By implementing those, you have a functional file system. Okay, you have a file system that is operational. So now, however, having a system that's operational is not always enough. Something else is important: efficiency and performance. Okay, what is the space efficiency, time efficiency of the algorithms, space efficiency of the structures that are used, and so on. Plus, how does the file system perform? Is the fast file system slow? Can read a file sequentially quite fast or slow, and so on. Performance is also important, right? So you may have a file system that is correct, that is operational, that's working, but it may be slow. Okay? So this is also important. Efficiency and performance is also important. So we will now talk about that a little bit. So efficiency depends on the disk allocation algorithms, how you allocate the blocks to a file, plus the directory algorithms, okay, how you structure your directory, how do you search your directory, what kind of structures you use, and so on, and the algorithms to search directory and so on. They are all important for the efficiency and for the performance, for the speed of the file system. What's important is we should have a disk cache. Basically, when you want to access a file, a portion of the file, that means the file system will access some blocks, one or more blocks from the disk. Okay? How long does it take to access those blocks? Will affect the performance of the file system. How long it will take to read that file or to access that portion of the file. How long does it take? Okay? That is affected by the disk's access speed and so on. All right? So how can we improve that? How can we improve that? The general approach to that is using a cache of disk blocks in memory. So this is called disk cache, okay, or buffer cache. So portion of the main memory can be used to cache, to store disk blocks that are accessed. All right? So if the cache is full of disk blocks, and if you need to bring a new block, then you can replace a block, of course. For that, you can use the LRU algorithm. The least recently used block in the cache can be removed, and a new block that is recently accessed can be put there, okay? So the same idea applies there, LRU idea that we have seen in paging, and that is also valid for hardware caches, right? Can be applied here as well. So this cache can be used actually to improve the performance. Why? Because when you put a block into the cache, next time you will access the block, you don't have to go to the disk. You can satisfy the access from the, you can satisfy the request from the cache. Access to cache is very fast because the cache is in memory. So if a block is in the cache, access to the block will be very fast, in the order of nanoseconds, maybe 200 nanoseconds, we don't know, but less than 1 microsecond, or at most 1 microsecond, okay? But if the block is not in the cache, if it is in the disk, then access to the block will be quite slow. Maybe it will take 20 milliseconds, okay? So therefore, having a cache is very important, and the cache hit ratio is important, of course, if you want to have a good performance and so on. Some other techniques can be used also to optimize and improve performance. Like, for example, the performance of sequential access. If you want to access a file sequentially, that means what happens? You start from the beginning of the file and read till the end, right? So what you can do is that the file is occupying some blocks of the disk, right? So you fetch the first block from the disk, then the next block, then the next block, okay? Actually, while doing a sequential read on the file system can know, okay, that the next block to be read will be something. The file system can know, can guess the address of the next block to be read after this block, okay? Because we are assuming that the read operation is a sequential. Then what we can do, instead of bringing the block at the time of the read operation, you can fetch the blocks ahead of their read, okay, ahead of time. So this is called read ahead. So read ahead means that you are bringing the block before it's actually being read. Okay, when I read this block, okay, I also bring those blocks into memory. Okay, and then after I completed that block, reading that block, I can immediately read the next block that is already in memory. Okay, so when I do a disk read, instead of just bringing one block at a time to the memory, I can bring, for example, 4 blocks at a time or 10 blocks at a time to the memory. Okay, because I know that those blocks will be read quite soon. Okay, this is called read ahead. So let's talk a little bit more about the cache. So we said that we have a cache, right? Buffer cache or disk cache that can be used to store disk blocks from the disk that are accessed. Okay. So for example, when you are reading a file using read and write system calls or fscanf, fprintf functions, right? What you are doing, actually the file system translates those read requests into block accesses. So those blocks are retrieved from the disk and they are cached here, okay? So if you read the file again, you are likely that you can find those blocks. It's like that you can find those blocks in buffer cache. So next time you don't have to go to the memory, to the disk, all right, while reading the file. So the next read operation may be quite fast and so on. Now let's look to another cache, which is called page cache. What is that? It's actually the portion of the memory that is storing the pages of the programs that are running, okay? Plus the files that are mapped into the address space of a program. With virtual memory, what we have seen, we have said that a file on disk can be mapped to the virtual address space of a process, to the virtual memory of a process. That means it can be considered to be as part of some portion of the virtual memory of the process. Then after you map it to the virtual address space of the process, that means you can access to the file by using pointer operations, by using ordinary memory accesses, okay? As if you are accessing your virtual memory normally with pointers. You can just, the mmap function will give you a pointer to the beginning of the mapped region of the virtual memory, and then using that pointer you can access the virtual memory region into which the file is mapped. Access to that actually is translated to the access to the disk file, okay? So now that means you are doing page references, virtual page references. Those pages correspond to the file content. So initially those pages are not in memory. So when you make a page reference, that page has to be retrieved. That means the corresponding code of the file has to be read into memory, into a page, and that page has to be put into a page cache, okay? So if you read the next portion of the file, next page, then that page may not be in memory. So from the disk it will be retrieved, content will be retrieved, and it will be considered as a page and put into the page cache and so on, okay? So while accessing a memory mapped file, okay, that means you are accessing your virtual memory pages. So they are retrieved from the disk, from the file content, and put into page cache, okay? So then, in this way, if you reread the file, then, or if you access the region of your virtual memory that is corresponding to the file, then your pages are already in memory, okay? Those accesses can be quite fast. So that as a result, we have a page cache that is caching pages, all right, corresponding to the file content, okay, for the files that are memory mapped, okay? For the files that are memory mapped and then accessed by using ordinary memory access methods like assignment statements and so on, using pointers and so on, okay? You have seen that actually in shared memory, right? You have mapped a shared memory into your virtual address space and access the shared memory content, right? Using a pointer. So this is the same idea. So then what we can have? We will have then two caches. A page cache storing pages and a buffer cache storing disk blocks, okay? So a memory mapped file that's mapped to the virtual address space of a program will be accessed in terms of pages. So the corresponding pages will be stored here. While accessing a memory mapped file, the pages will be loaded here from the disk. Those pages will include the file content, of course, okay? So the file on the disk will be considered as a sequence of pages. So when you access the pages, they will be retrieved from disk and put here, okay? But actually, when you access the pages while reading a memory mapped file, okay, or accessing a memory mapped file, you map it to your address space, you obtain a pointer, and then you use the pointer to access the file, right, to access memory region that's corresponding to file. That means you are making page references. So virtual memory manager now retrieves the corresponding page from the disk and so on, and actually, initially when you reference a page, it will be a page file. That page will not be in memory, right? So it will not be in page cache, initial reference to the page of a file. So what happens? We will ask to the disk subsystem to retrieve that page from the disk, right? So the corresponding block will be found. Usually the page size is equal to the block size. The corresponding block on the disk will be found, that's storing the page, and will be loaded. But the disk subsystem will load that page to here and then to here. So that means the same information will appear here and there, okay? If we are accessing a file using memory mapped I/O, okay? So of course you can also access a file using ordinary I/O. So you can open a file, read, write, okay? During this time you are not using the virtual memory management and so on, virtual memory subsystem. So you are just doing disk access. The file system will just find out the corresponding blocks and access those blocks, and those blocks will be buffered, cached in the buffer cache, okay? So the files that are accessed using ordinary I/O will have one copy here, the block, corresponding block, but a file that's accessed using memory mapped I/O, okay, then we'll have a copy here and then a copy there. So this is redundancy, right? So if we want to prevent that, we have to unify the buffer cache with the page cache. So a unified buffer cache uses the same cache to cache both memory mapped file pages and ordinary file system I/O blocks. So we have now a single cache, buffer cache, that can store pages corresponding to the files, and also that can store disk blocks corresponding to the files. Okay? So then memory mapped I/O and I/O using read-write system calls, they will use both the cache, both will use the same cache. Okay? So if, for example, this generates a page, the corresponding block number will be calculated. This generates, if this generates a page reference, the corresponding block number will be calculated, it will be searched here. Okay? And if, for example, you are accessing a file, the corresponding block number will be computed by the file system and obtained, and the block number will be searched first here. If the block is here, then you can satisfy the request from here. Basically, if it's a read request, that means you can give the block content. If the write request, your write operation can write to here and so on. Okay? But if the block is not here, that is needed, then you go to the disk and retrieve the block and put it here. Okay? Any questions? So these are issues that are important for performance, to have a good performance, so that accessing the files are quite fast. Okay, this is very important. You want to read a file quite fast, because disk I/O is a major bottleneck in the efficiency of programs while you are running a program. Okay, if it is doing disk I/O, your program actually will slow down. If it is actually opening files, reading files, so it is good if you can do those operations as fast as possible. If the performance of reading a file is good, it is a good system. Okay? So now, these performance issues, another issue is the recovery. What happens if there is a failure? It can be power failure, okay? So that suddenly the computer shuts down because power goes off, or a disk crash may happen, okay? So then these are the different things, right? So if a power failure occurs, what can happen is that due to the caching, some inconsistency may occur. Due to caching, what we have? We have the buffer cache, right? The buffer cache can cache what? It can cache file data blocks, but it can also cache metadata. Inodes can be cached, directory entry can be cached, and so on. It may be okay to lose the data blocks, but it may not be okay to lose the inode information and so on. So we may have data blocks of the file cached, inodes of the file cached, and so on. So metadata cached and normal data cached, right? Plus they have the corresponding disk values, right? So what we can have, we have the disk inodes or disk metadata, disk blocks, and we may have their cached values here, all right? So, of course, ideally we would like to have them always consistent, equal to each other. But that may not be always possible, because when you write something here into a page or block here, writing it immediately to the file system also actually invalidates the use of the cache, right? Sometimes you write here and you not write it immediately to disk. You write after a while, okay? So what happens if a power failure occurs during this time? So you have inode metadata here and cached metadata here, but the cached metadata contains the recent value, but here they are not equal to each other, okay? So at that time, before actually the modified metadata is written back to disk, a power failure occurs. Then you may have inconsistencies in your file system. You may have for example, directory entry, okay, pointing to a wrong inode, or you may have an inode for the file, okay, that is used, that's intact, okay, but the directory entry may be missing, okay? So these inconsistencies may happen when, for example, power suddenly goes off, or when you shut down your computer suddenly, okay? So what we can do is that we can do consistency checking. So there are some utility programs like fscheck and so on in UNIX. After a power failure, when you reboot your computer, you run that program, okay? So that it makes a consistency check, compares the data, the inodes, okay, the information in the inodes, the information in the free list or in the bitmap corresponding to the free list, the information in the directory entries, and checks whether they are consistent with each other, okay? If there is an inconsistency, it tries to remove the inconsistency if it can, okay? If it can still not remove, it can give a warning and so on, okay? So that you can be aware that there is an inconsistency in your file system. So this is the consistency checking, okay? The other issue is the recovering from disk crashes. How can you do that? The disk has crashed, okay? It has crashed, okay? For example, somebody has stepped over the disk and it is crashed. You cannot do, okay? You cannot recover the data. So if you want to be able to recover such situations, what you should do, you should take backups, okay? So there are some system programs that can take backup to some other media. So basically you replicate your data. So you can take the disk data and put it into a tape or to another disk and so on, okay? So when there is a disk crash, for example, you can recover the data by restoring the data from the backup system, okay? So we will talk more about this issue a little bit later. So let's have a break now.